of chemical reactions today. All right, back in the day, we talked about different types of reactions. I typically call this guy a synthesis reaction. That's what we label it in regular chem. We kind of liken this to like a marriage where two people get married, and then decomposition reaction, we liken that to divorce, where they're breaking up. Okay. Single ionic replacement. This was a single replacement reaction. Remember, you need to use your activity series for that. Okay. Back in chemistry, we talked about that being a team roster and how if you have a better player in the game, nice. If you have a better player in the game, okay, why is this acting like this today? Right. They did some sort of update overnight, I bet, and now I can't write on my board again. Great.
Gotta love it, Lippy. Gotta love it.
Happy Wednesday. It's an advisory day.
Oh,
Don't even.
I hate
All right. Let's see if this will work.
You guys are writing
No, it won't. It won't even let me write on here.
Did you say I give up?
I said dadgum.
Oh.
It's a southern phrase.
I know it's a southern phrase, but I thought you said I give up.
No, I said dadgum. Okay. Well, more and one way to skin a cat. We're doing southern phrases. Every time they switch stuff around here, it messes everything up. All right. So, when we were talking about these back in the day, we said that you had to look at what was getting swapped here. Okay? So, A and B. All right? If you look at your activity series and A is above B on that activity series, meaning it's more active, then A will replace B. Okay? But if you have a situation where B is above A, then this would result in what? No reaction. Okay? So if B is a better player, if it's more active than A, it's not going to replace it. Do you remember doing that? Yeah.
More active again.
That's beyond the scope of this course. Okay. One thing that would do that might be like, based on electronegativities and based on, it's just way beyond where you're at right now. Talk to Ethan. He might not. All right. So then down here, when we talked about these double replacement reactions, we had A and C. A was with B and C was with D. And I said that this was a messed up Maury Povich episode, right? Where they start throwing chairs and everything else. Because up here we had marriage and divorce. Down here, they're swapping around. It's like, oh, Lord. Just step back. Is this going to get ugly? Okay. There might be some sort of fight over that one. All right. So that was double replacement. That's ionic substances here. So we gave you an example down here. Lithium dumps chlorine and picks up sodium nitrate. Silver dumps nitrate and picks up chlorine. Okay. Then we had our combustion of a hydrocarbon. So here's your hydrocarbon. It's going to mix with oxygen, and you're going to form your carbon dioxide and water. And then I said, in reality, in real combustion engines and stuff, you're going to produce carbon monoxide too. And that's why you've got to make sure that you have proper ventilation, because your blood, your hemoglobin in your blood prefers carbon monoxide over oxygen. And so it'll pick up that carbon monoxide, and then you're not getting enough oxygen into your cells to be able to produce the energy that you need. Okay. Now, double ionic replacement is also going to include acid and base neutralization and precipitation reactions. All of these are considered to be redox reactions. Okay. So we call these redox or oxidation reduction reactions, except for a double ionic replacement. Okay. So those are redox reactions. We got to talk about redox. Redox is coming, you guys. It's coming. And it'll come back to you in the very last unit of the year too. So it's coming. It's not so bad. It's okay. It's not bad. Okay. Acid-base reactions. I'm just introducing you to the term today. I will get into what it is in the future. Okay. Acid-base reactions then. You guys have seen these before back in the day. I just moved you around. You shouldn't have done that to me. When I move you around, you should be okay. All right. So acid-base reactions then are going to, and we use the Bronsted-Lowry definition of it, okay? There's other definitions of acids and bases. I can't remember what the original one was called. We don't use it anymore, so it doesn't matter. Bronsted-Lowry, and then there's also, when you get into college, you'll probably do Lewis acids and bases, which are a little more complicated, okay? But for right now, we're just doing Bronsted-Lowry, okay? So be thankful. Thank you, AP Gods, okay? I just am telling you that the Lewis is out there so you don't get to college and go, well, Libby never told us about. I told you, you're just not doing it, okay? So acids are proton donors and bases are proton acceptors, okay? That proton is hydrogen. So they're just swapping hydrogen ions around, essentially. Am I boring you? Okay. So when we're looking at these, the hydrogen is going from an acid, in this case, over to a water and forming H2O plus, H3O plus. So this is H3O and it has a plus ion associated with it. Okay? I should bring my mouse over here to keep walking back and forth. It's hard to do this at an angle. All right. So we have, when we look at these, what you look at is you try to find the things that are alike. Remember doing this back in chemistry? You find the pairs, okay? So this guy here and this guy here look like they belong together, right? You see HCl here and Cl plus, right? See those? Find the pairs. Which one has more hydrogen of those pairs? Yeah. So this is going to be, where's my cursor now? Where'd it go? It's down there. So this is going to be your acid. And this over here then will be your base. Okay. Then, do you see how these two things look similar to one another? Which one has more hydrogen? This guy. So he is your acid. This one is your base. Now, the things on this side, we call those conjugates. So this is your acid, base, your conjugate acid, and your conjugate base. Conjugates just are on this other side. Okay? So in this example, water is acting as the acid and donating a proton to form H3O plus. This also has a single arrow going this direction. That means that this guy is a strong acid because all of your material is going to get broken up into ions. Remember, we have strong acids and weak acids. Strong acids and weak acids are different than concentrated acids and dilute acids. Okay? You could take this and have a super, super low molarity for it, for your HCl. It would still be a strong acid, but it wouldn't hurt you because it's such a dilute situation. Okay? As opposed to like vinegar. Okay? Vinegar is acetic acid. You could have very, very concentrated acetic acid and it would burn holes through your clothes and stuff, but it's still considered a weak acid because most of the material is going to stay in the acid form. So it's going to stay on this side of the equation. All right. Now, water can act as a, it's donating the proton. In this example, so I think it's the next example. Yeah. So the next example here, water is going to give that over to this ammonia. Okay. So in this case, it's acting, you've got an acid here and your base here. Now water is acting like an acid. If a substance is able to act as either an acid or a base, it's called amphoteric. Amphi means two different states, like amphibians are water and land. Okay, so amphi means two states, two conditions. Does that make sense? Okay, and this is, water is considered amphoteric. Not everything is. Water is a special one that can do that. Not everything can do that though. Good?
Yeah.
Okay. That looked like you're trying to wrestle with reckoning something.
No.
Okay. I missed my cue. All right. So, like I said, acids are described as either being strong or weak. Strong means that it's going to dissociate or separate into its ions. And all of it will. Weak means that it's only going to partially separate. And there's actually numeric values that you will learn when we get into chapter 8 that will determine where the threshold is for that. Okay? Because it's kind of a scale. Okay? Some are weaker, some are stronger than others. All right. Oxidation reduction reactions. I told you we'd be getting into these. These are going to involve the transfer of one or more electrons. So acid-base are proton donors and acceptors. This is going to be transferring electrons now. Good? Okay. So these are called reduction or oxidation reduction reactions. We call them redox. Okay. Oxidation is going to be the loss of electrons. Reduction is the gain of electrons. I know. How can an oxidation, or how can a loss, or how can a gain be a reduction? I know. I get it. Do I have a slide on here? Do I have a slide? I don't have a slide. Okay, here's how I remember it. Oil rig. Can you imagine the oil rig? You've got your oil rig. It's out here. It's like going up and down and up and down and pumping. Yeah, you know what an oil rig is. Okay. Oxidation is loss. Reduction is gain. Okay. Leo goes grr. Loss equals oxidation. Gain equals reduction. So you can imagine a fluffy lion over here if you'd like. However you want to remember it. So loss equals oxidation. Gain equals reduction. If you want to imagine your little lion, he's got his big fluffy mane out here, you know, with his lion body. He's got his tail running out here. But he's going grrr. He probably wants some legs, maybe. I don't know.
I don't know. I don't know if lions.
Did
can
that make it
stand
worse?
that.
I don't know.
I don't know. Oh, okay, that fixed it.
Yeah,
Whiskers?
you gotta have whiskers longer than the
Whiskers.
That
legs.
wrapped it up.
Yeah. Whiskers longer than legs.
That is class.
He's sitting there with just curling his whiskers around his.
You got a big mustache.
Yeah. So, yeah, art is not my forte, y'all.
It's also in a, like,
But there are some really cute, like meme kind of things out there if you go in Google Image that are a lot better than my drawings. So, my apologies. You can see that art was never my thing. All right, so we are going to look at this. We're going to try to see if this is an oxidation reduction reaction. Okay, so when you do this, you have to find the oxidation numbers for everything on here. Okay, so here you know that nitrate is a -1. Yes, Nick the camel. Okay, so this is a -1. If I have 2 -1s and I only have one of these, what charge must it be? It has to be a +2. My sodium, when you have just a single thing by itself, its oxidation number is 0. Over here, nitrate is a -1. This is in a 1-to-1 ratio with the sodium, so sodium must be a +1. You should also know that sodium is a +1 because it's in the first column on the periodic table. Everything in the first column is a +1 except for hydrogen because it can flip back and forth and be either plus or minus. But everything else, all the metals are +1. All right, so let's look and see what's happened here with our dear friend copper. Okay, copper has gone from a +2 to what on this side?
0.
A 0. So if it has reduced its number here, what has had to happen with the electrons? It gained electrons. So it reduced its value, which means that it's gained electrons. So it has been reduced. Okay. Our nitrate, did it change? No. So nothing happened with that. But our sodium went from a 0 to a +1. So what happened with it? If its charge was increased, it was oxidized then. Okay, which means it's lost electrons, right? I probably flipped these two around compared to that. I'm sorry that I got my columns mixed up. Now, this is what happens in batteries. Okay? Your batteries have a red terminal on them. Have you ever cracked the hood of your car? You see a red and a black on that battery? The one that's red is where this reaction is happening. That's why they colored it red back in the day. That's where your reduction reaction is occurring. Okay? All right. They call these oxidation reactions. It doesn't always occur with oxygen. Back in the day when they first discovered these and were creating them, it was oxygen that they were working with. And so that's why they called it oxidation. Because these oxygens were flipping back and forth and going different places. Okay? So that's where the term oxidation comes from. Now, if you remember back on your periodic table, back when you were young pups in here, I told you for the non-metals over here, just to ignore everything that wasn't a -1, -2, -3. That day is over. And you honestly really can't use the periodic table to help you. You have to use what you're given here to be able to figure it out. Okay? So you got to work with these substances to figure it out. So here are some ground rules. Okay? Oxidation numbers are always written above the element in question, just like I was showing you. They show the charge plus, minus, or 0. They're always written for one of the elements in the question, and the charge is always written first, followed by the value. Okay? Oxidation numbers can be fractions, but I've never seen that in AP Chem. So I'm just letting you know that when you get into college, it might happen. Okay? All right. Here are some additional ground rules. Okay? So elements always have an oxidation number of 0. So if it's just a plain element, even a diatomic element or something like this by itself, this is that Munster foolery or whatever it is, they're always going to be zeros. Hydrogen in a compound is always a +1, except when it is in a hydride. But again, we don't usually run into that much, so I wouldn't worry about that too much. So, trying to write on here without it flipping. There, that H should have been up here. Okay, here's a hydride. So you have this is your +1, so this would be a -1 for your hydrogen. Okay, pretty rare that you see something like that. All right, oxygen in a compound is always -2, except a peroxide. And I will get you on the exam on one of these, most of you. I'm telling you, it's on the exam. Okay, it was on the exam. I'm rewriting the exam. So we'll see if it still shows up there or not.
What?
I'm rewriting your exam for this year.
What is a peroxide?
Peroxide.
So, like H2O2 is a peroxide.
Why? Why? Just those.
And that's not always, but it will be always true in AP Chem.
She's not going to get me because I'm just not going to get the oxygen is -2.
I will come back to you with the peroxide thing. All right. Oxidation numbers of neutral compounds always will add up to be 0. So you've got 2 here at a +1, -1 at a -2. That's going to be a 0. Okay. Oxidation numbers of polyatomic ions will always add up to be the sum of that polyatomic ion. Did I lose you? Is this okay? Understand number 6? Everybody okay with 6? No? Okay. All right. Let's look at NO3 minus 1 then. Okay. Oxygen is a minus 2. Okay. So that means that oxygen side of NO3 is going to be a minus 6. The polyatomic ion overall charge is going to be a minus 1. So this side has to be what? Plus 5. Because 5 minus 6 is a minus 1. Okay? Which means if I've only got one nitrate, that has to be a plus 5.
Me too.
What's wrong?
Where did the negative 6 come
So oxygen's always a minus 2.
Okay.
I have 3 of them.
Okay. That makes sense.
So minus 2 times 3 is a minus 6. My overall charge of the nitrate is a minus 1, which means that this side has to be a plus 5.
That makes sense.
I only have one of them, so the nitrogen has to be a plus 5. And this is where all of those pluses, all the extra garbage that was on your original periodic table last year, that's where these numbers were all coming from. And I told you back in the day, if you took AP Chem, I would explain it to you one day.
Here we are.
Here you are. You have arrived. All right. Yes, you've arrived at your destination.
Hell is our destination.
I'm your tour guide.
Such a warm place.
All right.
You said this is on the like actual AP test.
Yeah. And well, and not only that, but like this is most, if not all, of chapter 9 or unit 9, because this is batteries. Like this is how your batteries work. Because they're creating electrons, guys. Huh? Yeah, it's essentially unit 9 is a battery. You guys actually build a battery in here and everything. Yeah. You're going to build a battery. Yep. So, yeah, you're transferring electrons. This is how all of your phones work. This is how your Chromebook battery gets recharged every night. Your electricity has to shove those electrons back over to where they're supposed to be. That's how your rechargeable batteries work. Your batteries in your remote work, okay? And eventually they transfer all the electrons out and they stop working because you can't reverse that back. But your Chromebook and your phone and your car battery and all of those things, they're able to convert those electrons back over to where they should be. So we have, we look at these oxidation numbers to be able to figure out what's going on. Okay? All right. You need to memorize your SNAP or your snack. Did you memorize that?
Of course.
Sodium.
Of course.
Okay. So here is your snack. S. Oh, I can't write on there. Dadgummit.
I tried doing it last night and I couldn't figure it out, and then I quit.
What did you try to do?
Mastercraft.
Didn't work.
So sodium, nitrate, ammonium, and then you can either call this a snack or a snap, however you want to remember it. I just don't want you to confuse potassium with phosphorus. So that's why I told you might want to do a snack instead of a snap. Okay? All right. So this is your general format for your precipitation reactions. They're just swapping partners and producing a solid in the process. Okay? All right. Sodium metal. Oh, where did that stuff come from? That was on the previous slide. That should be showing up here. There. Okay. Sodium metal is going to react with sulfuric acid. We're forming hydrogen gas and a solution of sodium sulfate. Write the balanced equation. Okay, so we've got sodium. You know why everybody likes sodium? Because it's sodium fun.
Oh boy.
All right, balance this puppy. I gotta put a, I got sulfate, I got hydrogen. I just gotta put a 2 here. We're good. All right. So when I am assigning oxidation numbers, I'm not paying attention to coefficients. Okay, coefficients, don't worry about those when you're doing your oxidation numbers. All right. I have this guy. What is his oxidation number? He's by himself. 0. Good. Okay. Now, I've got to figure out my oxidation numbers for all of this stuff. Shoot. Okay. So, what do we know about SO4 as far as its oxidation number is concerned? Nick the Camel 8. Clam supper in Phoenix? It's a -2. Yeah, supper has 2 vowels in it. SO4 is a -2. That means that this side must be a +2. I have 2 of them, so hydrogen has to be a +1. I have 2. My overall charge here is a +2. I have 2 of these, so each one must be a +1. +1 + 1 equals a +2.
Because we know that.
You know that SO4 is a -2. Nick the Camel ate clam supper in Phoenix. His supper has 2 vowels, yes? It is a -2. Okay? So this is a -2. We figured out hydrogen. Now we've got to attack our SO4. We've got to figure out the oxidation numbers of SO4. Okay? You ready? So I'm going to split this guy out now. I know that the whole thing has to be a -2. Oxygen is always
-2.
-2. -2 times 4 is 8. -8. Okay. Overall charge is a -2. So what does the sulfur have to be? 6. I have 1 of them. So the sulfur is a +6.
So anytime we see that
Sulfate.
sulfate,
Yep.
will it always be +6 and then -8 then?
Mm-hmm.
Yeah.
So if you have a eidetic memory or something like good memory, you won't have to redo that every time. I do not, so I typically have to. All right, over here, what is this hydrogen for its oxidation number?
0.
0. Hydrogen 0. Good?
Yep.
Okay. Over here, now, as Derek said, we've already figured out the sulfate. Okay? It's a +6 and a -2. We know that this side is a -2, which means that this side has to be a +2. We have 2 of these, so sodium must be a +1. All right. Now, we have to figure out what went on. We can see that our sodium went from a 0 to a plus 1. So what happened to my electrons here? Were they lost or gained? Lost. Okay. My hydrogen went from a plus 1 to a 0. So it became more negative, which means that it gained electrons. So if I lost electrons, is that oxidation or reduction?
Or no, it's not. Oxidation.
Oxidation. And if I gained electrons, it is reduction. Okay, oil rig. Oxidation is loss. Reduction is gain. Or Leo goes grr, however you want to remember it. Good? Still got time. All right. Reaction between nitrous acid. Oh, this is an easy one, guys. And hydrogen sulfide. Oh, wait. It's ion, though. Lipid. Okay, so this is going to become NO2 minus plus H2S. We are trading, we're moving hydrogens around. Okay, so the hydrogen from this acid is going to come over to this guy. So this hydrogen's just getting moved over to here. See that? So find your pairs. I got a pair here and a pair here. Which one has more hydrogen? This is your acid. This is your base. This guy ended up, now I've got my pairs here. This guy has more hydrogen. This is my acid. This is my base. And we just call the stuff on this side conjugates. I differentiate between the two sides. Easy enough? All right. Fun times, huh?